Hello everyone and welcome to the 2024 Advent of Code. This is day 13. We're going to be using Python to solve this one. And actually the majority of the solution is going to be a purely mathematical based solution rather than a programmatic one. That's because in part 1 you can do a programmatic one using greatest common divisor and certain algorithms. But in part 2 the search space becomes so large that it's infeasible. And when we step back a little bit, we can see that there's quite a nice solution, which I'll talk about. What I'm going to do is I'm firstly going to go over the problem, then I'm going to go over the way that the math solution and the mathematical logic behind it is derived, and then I'll be jumping into into part 1 solution and part 2 solution, which are going to be quite similar. So if you're not interested in the maths derivation, jump ahead later in the video. But if you are, just stick on for that. So this is the input that we're getting, and it's a series of games. So if we just take this one for example, each of these buttons, if you press button A, it moves the x variable up by 94 points, and it moves the y up by 34 points. And similar, this B button, x22 and y67. And we need to find a combination of A and B presses that if you press them a bunch of times, X ends up being 8,400 and Y ends up being 5,400. And then there's different games. And what we want to do is we want to say for each of these, figure out which ones are possible. And then there's like a cost function that we need to do. So the cost is 3 times the amount of A presses plus 1 times the amount of B presses. They describe that. I think it's around here. And so they give an example here. So you can see it takes, for this first one, you can do it in 80 A presses and 40 B presses. And so that would be 80 times 3 and then 40 times 1 for a total of 280 tokens or points. And then the task is to sum up all the points. So if we take this here, we can make this kind of a system of equations here. And so I've just written down what's on the page. And instead of the numbers, I've put A1, A2, I put B1, B2, and I've just got capital X and capital Y. And so you can imagine for this X here, X is a combination of B1s and A1s, and every time you press this A button, it adds an A1, and every time you press a B button, it adds a B1. So you could say, okay, for every time you press an A button, which is T1, it adds an A1 amount, and similarly, every time you press the B button, it adds a T2 amount of B1. So that's like this column, and similarly for the Y column. So you get these two equations. And what's nice is that A1, A2, B1, B2, X, and so this should be Y. It's a pair of linear equations, so there's no squares or anything. And we've got 2 variables. We've got T1 and T2. And so we should be able to solve them in the usual kind of way of eliminating one of them to find the other and then subbing it back in. So I'm gonna go through it. There's bits of algebra that I've skipped out, but I'll show you sort of what generally needs to be done. But one thing to note is that all of these numbers, so A1, A2, B1, B2, X, and this should be Y, they're all going to be positive, and T1 and T2, so the number of times that you need to press the buttons is going to be positive or 0. And in fact, now I'm looking at this, X and Y can be 0 as well. You could imagine if the prize is 100 and pressing A makes this go up by 10, that could be a viable solution, if it all worked out. Okay, so with part 1, we can rearrange it to get T1 on its own, T2 on its own like this, and similarly for part 2. So we have these 2 equations which is equal to each other. They're both equal to T2. Then we have these 2 here. And we know these are valid, and we're not dividing by 0 because B1 and B2 are both not 0. Because in our definitions here, this is B1, this is B2. Were they the ones? Yeah, B1, B2. and they're always not 0. They're always some number, some positive number. But for this case, it just matters that they're not 0. So we can set them equal to each other, and I've saved the space and the time for doing all the algebra. But if you times everything out and get t1 on its own, you get this. And now this is only valid if this bottom, this denominator is not 0, and we'll just make a note of that. We'll use that later in the code. But also, as an aside, if you're interested here, that a solution to this system of equations exists when this matrix is invertible, and that matrix is invertible only when the determinant of the matrix is not equal to 0, and this is the determinant of the matrix here. It's this off diagonal minus the main diagonal, and that is exactly what we have at the bottom. So this thing here, we can check to see if it's not 0, and if it's not 0, then we know we have a solution because we're going to generate one. But if it is 0, or you could say if this is equal to this, then we can't find a solution, and so we can just skip that game and go to the next one. Okay, so now back onto here. So now we've got t1. We can pick one of the two equations here to sub t1 back into to find t2. I've decided to sub it back into t1, so you'll get something that looks like this. And then again, saving all the algebra, this is what you end up with. And notice it's the same denominator, so we get the same argument. You know, if this thing is non-zero, this determinant of this matrix is not 0, then we can get t1 and t2. And I've kept this out the front here rather than putting it in, just to make that a little bit more obvious. And so now we can say, okay, t1, t2, what we've just worked out, is a solution to this equation, to this system of equations. You know, if we plug in t1 and t2, all the other numbers are there, and it'll give us x and y. Again, this should be y. But what it doesn't say is that these are integers. It says that they're just real numbers. They're just, you know, fractions. They're just decimals. They're just some number. I guess there will be quotient numbers, fractions, or potentially integers, but it doesn't guarantee it, and so that's something that we'll need to check. Okay, so moving over to the code, all I've done here is just read in here, and I'll try to be a little bit snappier with the reading in function here, because the real meat of it is past this. So what I decided to do, I said for each of the lines, I want to make a game out of it, and this game is going to be it's going to be this tuple, and this tuple as a list. So if the line is a new line, so if it's one of these new line characters here, then we know that we're at the end, and we're going to say the game that we've been making, we're going to append that. So games append game. What is games? It's going to be something on the outside here, something like a global list here, equal to that, append game. And if not that, then reset game to be just an empty list, and then continue to the next block. Okay, great. So I'm going to use regex for this, just because I feel comfortable using it, but you could use any other kind of system you wanted. But I'm going to do this first one a little bit slower for this first line, and then I'm just going to copy and paste and do the other ones. So it's going to look something like this. The plus is a special character. Then I want a capture group for the digits. And before we did something where we were, in a previous day's puzzle, we did something like this, where we had digits, that's one digit up to 3 digits, you know, so up to 999. What you can do is just have a plus there, and so that will get any number here. So any 1-digit number, any 5-digit number, any kind of number. There's a comma, then there's a y, again there's another plus, and then similarly another capture group here for that. And then we're going to say match A, and that's going to use this this library. So I'm going to import regex, and if it matches, so if the line, if the pattern matches the line with no white space, which you do with this, if that match occurs, so that's just going to be if that, so if it's true, then we're going to take our game object and we're going to append a tuple to it. And what is that tuple going to be? Well, we can extract everything from here. The 0th one is going to be the whole string. The first one will be this first capture group, and the second one will be this capture group. And at the minute that'll just put it all as strings, and I want them as integers, so I'm going to do that there. And now I'm going to quickly do the same for B and for the prize. Okay, so I've just copied them, and then what I want to do also is each time I've matched something, I don't want to check the rest of the things because I know that it can only be this. So I'll just continue to the next line, and I'll do that like this. And then one quirk of this is that when you get to the last game, we won't hit this again because it won't, there's not a line underneath the last one. So at the very end, there's going to be a game already made up, and I'm just going to add it like that. So if I was to print the games, you can see here there's the A values. Oh, if I go for this bottom one, here are the A values there, the B values, and then X and Y there. That's the X value, that's the Y value. Okay, and then to the kind of the main part of this, we're going to say for game in the games, we're going to extract all these things that we've just got. So A1 is going to be the 0th part and 0. And I'm just going to quickly do these now. Okay, so I've just extracted all of these. And now what we want to do is say we want to check that the solution exists. And we can do that with the determinant that we had here, making sure that this thing is not 0. And then after we've checked that it does exist, we can go ahead and calculate T1 and T2. And then we can check if T1 and T2 are both integers. Great. So how are we going to check to see if the solution exists? Well, there's this determinant that we checked out before. So it's going to be if A1 B2, so A1 times B2 is equal to A2 B1 is equal to A2 B1. And remember, this is the same way as writing like that, but I've just chosen to do it like this. If that's the case, then we know that there's no solution for this game, and we can just continue to the next game. Okay, so now we're confident that there is a solution to this game, and we can go ahead and calculate them. So T1, we found here, is going to be B2x minus B1y, so B2 times x minus B1 times y. Just check that. Yep. And this is going to come up often here. So I'm going to calculate that at the top. I'm going to call that determinant of the matrix. And that is going to be A1 times B2. So this thing minus this thing. And we know this is not equal to 0 because we've just checked here. And t1 is that minus that. Sorry, divided by that. So that's the numerator, and the denominator is that. And I'm going to do regular division here rather than integer division, because I don't want to round down or anything. I want to find exactly what this is. And t2 similarly, if we look here, is going to be xa2 ya1. So x and a2, y and a1, that's going to be plus there. It's also over this, but then there's this minus 1 here, so I'm going to have that like that. And I'm sure it would work itself out, but I'm going to put them around like that. And so now if I was to print t1 and t2, can see here, I'm just not going to print the games. You can see here we've got a solution for all of them, and in fact there must be a bug, so we'll check that because this should be 40. But this, when we debug, will be a integer, so I'll just debug now. Okay, that's the issue there. I copied over wrong here. This plus here should be a minus, so that's just copying it over wrong when I put it onto this sheet. So this plus should be a minus. If we run it again, we can see here, we know that the first one and the third one, because it says so on the page, have solutions, and these two don't. And we can see here that that's because these are integers and these are not. And so all we need to do is check for t1 and t2 to see if they're both integers. And how we can do that is quite easy actually, because Python has a built-in function. We can say if t1 it is underscore integer, and t2 is an integer as well, so that's this case and this case, well, then we can go ahead and add to a total score, which we're going to make up here. And the total score is going to go up by 3 times, so I'm going to add to it 3 times t1, and then it's going to go up by t2. And then at the end of it, if I print the total score, and I don't think we're printing anything else, we should get 480. I'm okay with the 0.0 there, but if you wanted to get rid of it, you could just cast it to be an integer there. So 480, and if we check the example, it's 480. And so if I now do it for the real data, I get 3, then 3 9s and a 6, and that's what we get here. And then moving on to part 2, it's really similar to part 1 in that instead of having 8,400, it's now got this massive number added to it. And this is the thing that makes a more programmatic approach infeasible, because the search space for these numbers becomes huge. You end up essentially with 2 numbers, with a t1 and a t2, and you're increasing one and decreasing the other, and you're trying to find a sweet spot. But the space is so massive that it takes so long to even finish one game, and in the input, I think there's 50 or so games, so it's just not feasible. So all we're going to do is it just says to add this number to x and y at the beginning. So we're just going to say, okay, when we get these, x is going to be equal to that number plus what we had before, and y is going to be equal to that number plus this one before, and then we can just simply add x and y to this. And then if I go back to the example, the example doesn't tell us the score that we should get, but what it does tell us is that the second and fourth one should have solutions, And so what I'm going to do is I'm going to print, just to show you T1 and T2. The first one no longer has integer solutions, and neither does this one, but the second one and the fourth one do. And that's what it says here. It's now only possible to win with the second and fourth. And so this would be the answer to the example. But if we go ahead and do it with the real data, and I'm not going to print here anymore, we get this number which ends in 867, which is what we get here. So hopefully you enjoyed that. A bit more of a mathematical approach rather than like a programmatic approach. And I think it's good to step back sometimes and think if there's a possible solution for this. You know, when you get something that's when it's two equations and two unknowns, and everything's quite nice, you know, in terms of like there's no squares or anything, you can generally find solutions. Okay, so that's it for day 13. If you did like the video, please do like and leave any comments for any suggestions, and please subscribe for the rest of Advent of Code. I'm aiming to do a video per puzzle, even though they might not come out on the day that the puzzle comes out. Great, and I will see you again for day 14.